So yeah, thank you for having me here. I'm really happy to share this work with you today, especially in this kind of friendly and inspiring environment for open tools. So my presentation may actually fit a bit better with what we saw in the previous session. So maybe think of this as a continuation, okay? But okay, so as many of you know, developing pull sequences is not an easy task, okay? And traditionally, it has involved vendor-specific and closed tools, which has made the workflow less accessible and not very reproducible, okay? But luckily, over the past few years, and as we have been already seeing throughout today, the community has put a huge amount of effort into changing this, building an ecosystem of open tools for sequence design. Okay, so a major step forward was, of course, PullSec, which introduced an open and standardized file format for sequences and MATLAB libraries compatible with this type of files. And then we have more recent tools, by the way, most of them compatible with PullSec, that focus on usability by means of graphical interfaces. Okay, so the most relevant and recent nowadays, and in fact, which have been presented here, are MTRK, okay, which I've learned today that is pronounced MTRAK. So yeah, and which has a very intuitive graphical interface, and Gamma Star, okay, which actually runs as a web application. On the other hand, there are also very useful open software tools for simulating MRI, okay, such as Gembris, okay, is a long-standing and very powerful simulator, and also has a sequence development tool, okay, or MR0, which integrates simulation with machine learning workflows. They have presented this like some years ago. So, and there is Comma, which is a fast GPU optimized simulator whose motion capabilities have been actually presented by Carlos like an hour ago. So we are, you can see all this environment, and I'm forgetting things, I'm sure of that. But what becomes especially powerful is when sequence editors and simulators connect directly, okay? Because that gives you a full pipeline for prototyping. And this is even better when it happens inside a web browser. That means that you don't need to install anything in your computer. And we are already watching this happening. And in fact, again, MTRAK along with Comma MRI are integrated into CloudMR, which is a great environment, and has also been presented here. And there is also Gamma Star, which can be easily connected to MR0. Okay, so after looking at this great ecosystem, I'm presenting our actual contribution to it, which is more of a minimal web-based demonstrator that follows this complete pipeline approach and works out of the box, let's say that. So it's called MR Sec Studio, and we have been working on it with the following aspects in mind. We want it to be easy to use, okay? We want it to be suitable for research, this sequence prototyping that we have said, but also suitable for education, as it could be a useful tool, for example, to explain pull sequences and MR phenomena to physics or engineering students or even radiographers at some point. We want it to be fast, no matter the device, open source, of course, and reproducibility oriented, which means that we want users to be able to share the sequences they create with other people. Okay, so with that in mind, let me give you a sense of how everything is put together, a very high level overview. Okay, so the tool is structured like any other web application. First, we have a front end that's the user interface you actually interact with in your browser. And by the way, it's responsive, so you can even run it from your phone, just in case you ever feel like developing sequence from your mobile phone for some strange reason. But in fact, it might be useful for students or for testing simple experiments using it from your phone. And then we have the backend, okay, which runs on a server through an API the front end gets to the backend's resources, like the MRI simulator. This MRI simulator is specifically Comma, okay, Comma MRI. And we have another resources in the backend, such as the database, okay, in which sequence and phantoms can be stored for simulation. So going one step deeper, a big portion of the front end is written in Qt, okay, which is a C++ framework for user interface development. And thanks to WebAssembly, you can compile that C++ code so it can be run efficiently on the browser. And at the same time, the functions that interact with the server are written in pure JavaScript, okay? So then on the server side, everything is written in Julia, probably not too known language, but which is quite efficient and fast and has been introduced before also by Carlos. So actually, the Comma simulator is a Julia package, and also the API in the server is another Julia package called Oxygen, and this is the one that communicates with the front end. So a basic workflow example illustrated in the figure would be to plot the time diagram of the sequence that we are designing. And for this, we need to send the sequence information to the server, and Comma creates the plot, and this plot is then rendered back in the front end. Okay, so something similar would happen with a simulation. We would send the sequence and the phantom information to the server. Comma would carry out all this heavy stuff, all this heavy computation, and the result would be returned to the front end. Obviously, all this happens behind the scenes. Okay, the user experience might actually look like this. Okay. Oh, this just got broken, but what happens, okay, is the user doesn't have to know which device is running behind the scenes, okay? So it might be thought to be running on a powerful server, but in our case, and for now, it is running on a simple PC without even a GPU. Okay, but that's actually a good thing. It means that the app can run even on a simple PC, and once a GPU is available, Comma just uses it automatically. So everything runs faster with no changes needed in any part of the code. Okay, so now we have seen how it has been implemented. I want to show you how to actually use the tool. Okay, so let's see. So this is the interface at a glance, which, as you can see, is divided into different panels. We have added tags from A to K to these panels to better illustrate them now. So panels A to G handle sequence design. Okay, so panel A is the timeline where the sequence is constructed by means of building blocks. B is the block palette, from where you can add new blocks to the sequence. C stores the group of blocks that may be created by the user. D shows and edits the parameters for the selected block. E sets scanners the parameters of the scanner, like B0 or the maximum RF or gradient strength. F is a small scripting area for global variables and expressions, which can then be used when configuring the sequence blocks. And G is a free let me check a thing. Okay, yeah, sorry, I continue. Yeah, I was talking about, yeah, the panel F, okay, about it. It is, yeah, a scripting area, okay, like that allows you to define global variables and then use that global variables when configuring the blocks. And G is a free text field for metadata or notes about the sequence, like just simple notes, okay? Then the panel H selects the phantom, and pressing simulate send this phantom along with the sequence to the server. Then panels I to K are the visual outputs, which show respectively, the sequence diagram, the phantom, and the simulation result. Okay, so now let's see it in action with some simple examples. Simple, but enough to show how you can build more complex things in top of them, okay? So in this first case, we have just created a gradient echo EPI sequence by using 4 consecutive blocks. First, an excitation block, which contains the RF pulse and the slice selection gradient. Then a so-called dephase block, which contains the slice rephasing and the pre-phasing gradients. Then a delay to achieve a certain echo time. And then the EPI acquisition, which is a preset block, but which could also be made of consecutive dephase blocks. Okay, so we can see that in addition to running the simulation on the selected phantom, the interface also displays an interactive diagram of the sequence as well as the 3D slice selected by it. Another use case is the loading and adjustment of a spin echo sequence to obtain, for example, different image contrast and weightings. So as you can see, okay, let's see if this starts. Okay, as you can see, we can visualize the phantom with the 2 viewer modes. The first is an slice viewer, and the second is more of a volume rendering. Then you can see how in this scripting area we have defined variables such as the echo time of the repetition time. We have set them to be the appropriate values for getting first a T1 weighted image. Okay, if we tune these values with another appropriate values, we can get a PD weighted image. And last, with long TE and long TR values, we get a T2 weighted image. Okay, so yeah, that's very nice, but the title of this presentation was Exploring Motion Effects, and we haven't actually seen any motion yet. So let me show you the next example to illustrate that. And this is an experiment where we will start with a cylindrical phantom with fluid flowing inside. It's similar to what Carlos presented. And first we visualize the phantom with both viewers to get a sense of the geometry. And in the 3D view, we can also see the flow itself, okay? If you see, we can see the spins flowing, okay? Then we can load the GE EPI sequence and check its diagram. Okay, once we have, we are seeing that diagram, we can run the simulation and we can see how the wall tissue and the lumen share the same T2 and PD, so there is no intrinsic contrast. Both appear with the same intensity, but now we have loaded a balanced steady state free precession, and after watching its diagram, we can simulate it and see how now there is a difference of intensity between this wall and the flowing spins. Okay, this is due to the time of flight effect. So this example have shown how easily you can swap sequences in the interface, okay, and how the simulator captures contrast that comes out purely from motion, okay. So this opens like a lot of possibilities to maybe recreate more complex experiments, or yeah, just to develop and prototyping sequences. So let's continue just with the conclusions. And just to conclude, we have introduced a web-based application that brings the whole workflow of MRI pulse design and simulation into one place, with an interactive easy to use interface on the front end and the physics powered MRI on the back end. Okay, the platform delivers a smooth and responsive experience while still providing accurate simulations. And the tool is designed for a wide range of users. Okay, from radiographers to MRI researchers, and even supports motion inclusive simulations. So overall, it's versatile, accessible, and extensible resource that makes MRI simulation easier to get into, okay, and opens up new possibilities for teaching, but also for testing and research. So this application, of course, is still a young project, and there is plenty of room to grow. One of the first things we want to do is to extend the block palette. Right now it is quite compact, okay, and adding some flexible elements like arbitrary shaped waveforms will really open up what you can prototype. And along with that, we will like to expand the set of preset sequences just to make it easier to start from something really ready-made. And another important step is full PulseSec 1.5.1 compatibility. Like Coma is already compatible with earlier PulseSec versions, and we are now working on supporting this latest version completely, both for reading, okay, and for writing. So once Coma has that full support, the editor will automatically benefit from it as well. As I say you, we have already 2 GitHub peers working on it, and they are almost finished. Then on the simulation side, we want to expose more parameters, both from the scanner and to the reconstruction, and to give the user more control over phantom motion. Okay, so you can even define, like in a easy way, this motion. For dynamic acquisitions, we are planning a better visualizer that can handle multi-frame simulation outputs. And then there is all the infrastructure work, like improving server resource management, so we can move from a prototype to something closer to a production environment. But again, this is not very easy or very direct. Then, of course, general usability improvements, documentation, for sure. We have to work on that, as it is essential nowadays, and maybe many more improvements that may come up from people using the tool. Okay, so here are some resources if you like to play with the tool first. Okay, so yeah, the one in the left takes you straight to the web application. As I say, no installation is needed. And the GitHub repository on the right is available if you want to check the code, fork it, and basically contribute. Okay, I'd really appreciate any feedback to this. And yeah, that's all. Thank you very much for your time and for your attention. And I'm open to questions.